One example is G. The force of gravity between any two objects, for example, the Sun and Venus, depends on 1 over the distance square. The Sun attracts Venus, and Venus attracts the Sun back, and they rotate around each other. They orbit around each other. Okay? And this G here is a fundamental constant. Fundamental means it applies to all objects anywhere in the universe. For example, if I write the force between the Earth and the Moon, the formula will have mass of the Earth, mass of the Moon. But the constant G in front is the same G as I write here between the Sun and Venus. Okay? So it's a fundamental constant. It's true for any situation. It is the constant that describes in our units, the MKS units, how strong gravity is. So that's important. That's fundamental. Okay? Another important constant is this. We will learn in the course that there is a property of particles called charge. This is responsible for all electric phenomena. And a proton and an electron attract each other with this electrostatic attraction. If you don't know what it is, don't worry. I'm not trying to teach you about it. We will do that later. I'm just using it as an example. Okay? Proton, electron attract each other, and the attractive force depends on 1 over the distance square. It depends on their charges. Their charges are plus E and minus E. They have the same magnitude of the charge, same number, times a constant K in front. So the force of attraction in an atom, in a hydrogen atom, proton, electron, has this combination of constants. Not just K, but I put the E square in there, because in any atom, maybe it has 5 protons, then I put the number 5 in front. But charge of each proton and the charge of an electron is the same in any kind of atom. Hydrogen, helium, boron, whatever you want. Okay? So K times E square is going to be fundamental, because all atoms all over the universe are the same kinds of atoms. Alright? So K over E square is going to be a fundamental constant. What does it describe? It describes how strong the electrostatic force is. Okay? Now I'll mention another fundamental constant, which most of you have not heard of, and we will learn about this one also later in the course. This is pronounced H bar, because of this sign on top. This is a fundamental constant. We'll learn about it later, but it is the constant of quantum mechanics. And what it describes is, in quantum mechanics, inside atoms, we find from experiments that electrons and protons are not just particles the way we think of a piece of stone or a bullet. They are sometimes like particles, sometimes they are waves. And this constant is the fundamental constant that describes when and to what extent some object is behaving like a wave, and to what extent it's going to behave like a particle. The very strange, funny relation between particle properties and wave properties is described by this constant. Okay? Just know this much. We don't really understand it yet. We haven't discussed it. But I'll just use it here to give examples. This is the Planck constant. And there's another fundamental constant that I'll mention, which we already saw in the first lecture when we discussed Einstein's formula for adding velocities. What was that constant? The speed of light. Why is that a fundamental constant? Because, as we discussed, it is not just light. It is the speed of all kinds of electric magnetic waves, like radio waves, X-rays, ultraviolet, whatever. Okay. Moreover, as we will find later in the course, this speed c comes up in fundamental equations called Maxwell's equations in a way that does not depend whether the experiment is done in a train or on the station platform or where. Okay? It is a velocity that appears in the basic laws of nature that does not depend on who is observing it, at what velocity. So it has this funny property, the speed of light, that two different observers measuring the speed of light, and these two guys are moving with respect to each other. Okay, I'm at rest and somebody is running past at 50 kilometers. No, it's bad. Somebody is running, so it's maybe 5 meters per second or something. Whatever, okay? We both measure the same c. So it is a fundamental constant. It's a constant velocity that appears the same to everybody, no matter what that person's motion is. Okay? So it's a fundamental constant. Now, next thing I'll do in this example is to figure out the dimensions of the fundamental constants. G, m1, m2 over r squared equals a force. This is how we define the gravity, how the observations show us where the gravitational constant appears. Okay? So to figure out this dimension from this result, that it gives you how strong the force of attraction is between the Earth and the Moon or whatever, okay? Then we must know something about force. We are just beginning the course. We don't know what force is yet. So I just give that to you, okay? Force is the property that affects how motion is changed, and as Newton discovered, if there is some attraction, repulsion, some other objects are affecting this object's motion, then this effect, the force, will give you the mass times the acceleration. Okay? This is acceleration. And what this thing is this formula is Newton's second law. Again, don't try to understand it because I'm not teaching it yet. I'm just going to use it as an example. If you have never heard of it, don't worry. Okay? So F equals ma. What I've used it for is to figure out what the dimension of force is. F equals ma is the general law of motion that applies for all kinds of forces. So it tells me what kind of quantity is this force, what's its dimension. Okay? So dimension of force is m mass. Now what is the dimension of acceleration? We just figured it out. L over. Okay. And our fundamental dimensions are